Hello, welcome to today. We're going to work on lesson 2.5 for quantitative reasoning. It's all about the great tech battle, which we've actually been doing some tech things already in Desmos. So have your Desmos out and open today. We're starting here on page 189. As you can see, it's called the Great Tech Battle. And the quote today says, "One machine can do the work of 50 ordinary men. No machine can do the work of one extraordinary man." Albert Hubbard. So we have been talking in some ways about how two variables could be related. So in lesson 2.3, we talked about how the value of your car could go down over time. So time and value are related. And we talked about in the taxi cab example about how the more miles that you drive, the more the taxi cab costs. And then in 2.4, we worked on some examples as well about the more pizzas that you buy, the cost goes up. And so now we're going to talk about some situations in life, variables that where there could be a linear or exponential relationship, but it might not be perfectly related. So all the ones we've done so far in unit 2 have been perfectly related in a linear fashion. So let's look at the bottom of page 189 here. It says, in lesson 2.4, we examine the relationship between calories burned and weight loss. So if you did the extra example at the end, you would have done that one. So it says, while we needed to study data to model the exact nature of the relationship, you're probably able to figure out that the two quantities are related in some way. There are many quantities that seem like they might be related, but it's not clear that they really are, or if so, how. So it would be nice to have a way to study relationships, if they even exist, between data sets. Fortunately, the lovely folks who program spreadsheets and graphing calculators have done most of the heavy lifting for us. Still, in our continuing quest to not rely on technology more than our brains, it's a good idea to think about when quantities are likely to be related in some way. So, question number 1 has A, B, and then there's C and D, I believe, on the next page. And they're asking us to decide if you think the two quantities are likely to be related numerically and explain your answer. So it says dollars spent by a political candidate and the number of votes he gets. And I would say yes. The more advertising and phone calls, the more people will know that person, right? Him or her, and vote for them. So yes, I would definitely think that there's a relationship with that. B says an adult tests subject's height and IQ. So maybe there's a relationship, but I don't think so. Your height should not predict your IQ because there's very small people that are very intelligent. Letter C says a person's height and shoe size. So they do think that there is some relationship between these two. The taller you are, usually the larger your shoe size. Okay. D says the age of a car and its resale value. And there's a definite relationship because we saw that in lesson 2.3, that as the age of the car went up, the resale value went down. So we've already seen that one in an example. Okay. So here we are. Question 2, it says, is there a relationship between the total fat in a fast food burger and the total calories? The table here lists calories and fat information for a standard burger at a variety of fast food restaurants. Begin your study of this question by drawing a scatter plot based on the table. So for now, We are going to use Desmos, so you'll want to put this data in Desmos, but right now I'd like you to graph it on your paper because we're going to do something with it by hand. So you'll need to put it on your paper and graph, take a minute and do that. And it should look something like what I have here. Once you have that drawn, let's go to the next page. It says, the points on your scatter plot don't form a straight line, but there should be a linear trend you can observe. Use a straight edge. I'm going to use a piece of paper to draw a line that you think looks like the best fit for your scatter plot. Note that it's possible that the line that fits the data best doesn't go through any of the points. So I want you to draw your own line. I'm going to draw my line. Now, your line may or may not look anything like my line. So I'm going to draw. Don't look. Okay, there's my line. And my line really only went through one point. Oh gosh. Okay, so you should have your line drawn. We did that. Identify. Now, number 4 says identify 2 points on the line of best fit that you drew on your scatter plot and use them to find an equation. Okay, so find an equation. We have to have our slope m. So we need our change in y over our change in x. So the 2 points I'm going to choose. Now it says identify 2 points on the line that you drew. So don't pick 2 of the points here of the burgers and their calories. You want to pick 2 points that are on your line. So I'm trying to be strategic and find 2 points where these grids cross, so it makes it easy on myself, but you might have to do some estimating if you don't have any. So I have one here at 16 and 400, and it looks like I have one here at 10 and 250. So I have 16 and 400 and 10 and 250. Okay, so I have to find the slope of my line with those points. So I'm going to take 400 and subtract 250, and that means I have to use 16 and subtract 10. So that is 150 divided by 6. And so my slope is 25. And I'm going to remember what this is. This is 25 over 1, and I'm going to remember my units. So my Y units here are calories. So this is calories, and this is fat in grams. So this is fat. Okay. So I have my slope. So my goal for my equation is I need to have these pieces, right? My parameters are slope and y-intercept. So I have my slope as 25, and then I need to fill in my y-intercept. So my y-intercept, to find that, I'm going to take my equation, or my 25, and I know a point. So I'm going to use a point. So I know that 400 equals 25x. And the x goes that 400 is 16. So I'm going to put 16 in for x, and I can figure out what b is. And I could have used 250 and 10, but I'm going to use my point of 16 and 400. So 400 is my y, so I'm replacing y with 400. My slope is 25, and x is 16. So I know this is a true statement because I found it on my line right here, 16 and 400. And I'm going to solve for the b that goes with it. And it should be, I went all the way across. So mine should be about 0, 0, somewhere around here, right? It should match this. So 25 times 16 is, oh my gosh, it is. This is exactly 400. So if I subtract 400 from both sides, my b is 0. I've done this problem several times in several semesters, and I've never guessed 2 points with that. That's kind of weird. So my b is 0. So my equation is y equals 25x. Now, I'm going to show you, I've done this before. And I'm going to show you the guess I did last time. This is the guess I did last time I did this very same problem. My slope this time was 33.3, and my y-intercept was a negative 99.8. So you can see how I did this one. There was my slope. My 2 points were 6 and 100 and 12 and 300. And then I used 6 and 100 right here, along with my slope of 33.3. I multiplied those to get 199.8 and subtracted 199.8 from both sides. And I found that my y-intercept here was a negative 99.8. So my curve was much steeper then because it was way down here. I think I used this point and this point up here that time, something like that. Okay, so you've got your equation. It says, as you've just discovered, we can use a couple of points in the line and some algebra to find the equation of the line of best fit. Then, as we'll see shortly, we can use that equation to study the quantity. But the weakness in this process is that the line of best fit we drew is just a guess that we got by eyeballing the graph. Fortunately, calculators and spreadsheets have built-in formulas that will find the exact line of best fit for a given data set. The procedure is in the following box. Now, if you have a TI-84, you can go ahead and use this procedure. We've been using Desmos, and Desmos is very, very simple. So go ahead and flip your page to page 193, okay? And we're going to go through that. So when it asks for the line of best fit, it says use a procedure in the using technology. We're going to use our own Desmos to find the line of best fit. So line of best fit, and this is in Desmos. We're going to go to Desmos and enter our data in a table, and we are going to use y1 tilde mx1 plus b. So this right here is when we have data. When we have data points and need to find the line. So you should have this written on a separate sheet of paper because this is going to be on your note sheet for the midterm. Okay. So if your data is in X2 and Y2, you're going to have to use X2 and Y2 right here. So I'm going to go to my, I'm going to go to Desmos here to share it with everybody how to do this. And here is my Desmos. So I have my data in, and I'm going to hit my magnifying glass, and there is my scatter plot. It should look very much like we already did in our paper. And I'm going to go to the next line here, and I am going to type in just what I had on our paper. So it's going to be right here. It's going to say Y1, and the tilde is to on my key calculator, or my keyboard is to the left of the 1 key. And then I'm going to type X1 plus B. And look what pops up. Now, we've been doing this a couple times in our other lessons. I brought it up, but this is our formal time we're doing this. So our M, so on number 5, you should write in your paper off to the left, M equals, And notice they gave us parameters. So I had you write parameters the other day in another lesson. So the parameters for a linear equation are m and b, our slope and our y-intercept. M is our slope, b is our y-intercept. So I'm going to go back to my paper for just a minute so you can see what I'm writing. So m is our slope. I'm going to write that. And it is 20.76. I'm using 2 decimals. It says round to 1, so we'll use 20.8. And then our y-intercept, I'm writing them off to the side. B is 41.4. Okay, so we're going to put it in the equation. So y equals 20.8x plus 41.4. This is the line of best fit. The line of best fit for our data. Okay. Now, how do we know it's a line of best fit? So they're not asking us about this until later on. Okay. And it's actually question number 10, but I think it's appropriate to go to it. It's called our correlation coefficient R, and it's the lesson check. So, you know, on number 10 on page 195, I'm skipping there because it's up on our Desmos screen. So on your Desmos screen, you're looking for this, R equals, and I'm going to go there just to point it out. There it is. There's an R squared. We do not need that right now. We need the R. So write down the R on your paper for number 10. It's 0.8984. This is your lesson check, and you can just enter 0.8984. I think, I can't remember how many decimals it says in JetNet, but you can do unlimited tries. But this is your correlation coefficient. So let's go back to our paper. We want this, in other lessons, I've mentioned this before, but I'm going to tell it again. We want this to be as close to 1 as possible. We want this to be as close to 1 as possible. Now, the other times I've done this and pointed it out, we're with perfect data, and so our R was 1, but now it's not going to be perfect. So this is pretty close. So R bigger than or equal to 0.8 is good. Okay, so this tells us, let's write this in a different pen. This R tells us our line of best fit is good. Okay, so it's good to use to make predictions about our data. That's what this tells us. So you're going to need to know how to do the correlation coefficient for your I think your 2-3 worksheet actually brings it up. And I brought it up before, but I'm bringing it up again here. So following along on page 193, we found our equation by hand. I found the equation of best fit. We all should have the same here. This is 41. It says, use your answer to question 5, the line of best fit, to predict the number of calories in a Whataburger, which has 25 grams. Okay, so 25 grams is the X. How does the answer compare to the number of calories predicted by your own line of best fit in question 4? And this question 4. So we did question 4. We just said we're going to do the line of best fit prediction. So line of best fit. So Y equals, and it's 20.8 0.8 times 25 grams plus 41.4. So we can do it by hand. We can also do it on Desmos. I'm going to show you that in a minute. So 20.8 times 25 is 520 plus 41.4 is 561.4. So that's using the line of best fit. So Sarah's line. So you need to go and use your equation. So my line was 25x. Remember, there was no Y-intercept. So for me, I've just got 25 times 25, which equals 525 grams. Oh, 625. I misspoke. Mine is 625. So I definitely overestimated. Mine is much bigger. Okay. So you can see, I'm going to go back to my Desmos. So you can see how this would be done in Desmos. So in Desmos, if I wanted to find 25, I would go over here. I could click on the line that I predicted. Oh, whoops. I want to make sure I'm sharing the right line. If I am. Okay. So I'm going to click on my line of best fit, and I'm going to go to where X is 25, which is all the way up here. So at 25, you can see that it does predict what we came up with, 560.31. That's what we are, because of Desmos is using more decimal places than we are, so ours is slightly off the one we did by hand. So let's go back to number 7 on our paper. Number 7 says, a classic roast beef sandwich from Arby's, so it's not a hamburger, but a classic roast beef sandwich from Arby's has 360 calories and 14 grams of fat. What is your line of best fit predict for calories? Is this expected? Okay, so if we use the line of best fit, and we did 20.8 times the 14 grams plus the 41.4, we would get 332.6. Now it says, is this expected? I would say no, because we probably shouldn't be using a line of best fit for hamburgers to predict a roast beef sandwich. So I would say no. Okay. And that's because I would say you should not use a line of best fit for hamburger fat predicting calories versus a roast beef sandwich. Okay. So at the bottom of page 194, they introduce this correlation coefficient. It says if your calculator is not displaying, we're going to do that. It says this number right here, this is important. This number measures how well the line seems to fit the data. The closer R is to 1 means a positive slope, or -1 is a negative slope. The more accurately the data you entered can be modeled using a linear equation. Here are some examples. So this one is, I would guess, is a very close to a +1 because it's going uphill and the data is pretty linear. This one, I would say, not a good fit. It's hard to tell if it's kind of moving uphill or kind of downhill. So number 8 says, one of these scatter plots has a correlation coefficient of 0.19, the other has a correlation of 0.82. So what we just mentioned here would be filled in. So this would be the one with 0.19, not very good. And this would be the 0.82. It's a pretty strong fit. Okay. We're going to skip 9. We've already talked about other relevant things. And then we talked about 10 as our lesson check. Everybody has that filled in. Okay. Now, 11 says, based on all the work done in this activity, how strong do you think the relationship is between the number of grams of fat in a fast food burger and the number of calories in it? Make sure you justify your answer. I say there is a strong relationship using the scatter plot and the R correlation coefficient. Okay, so an important note on lines of best fit. Hopefully you noticed right from the beginning of our study of burgers that you can't draw a straight line that goes exactly through all the points. That in turn means the predictions made by your equation for any sandwich are unlikely to be perfectly accurate. This will almost always be the case when finding a line of best fit for a data set with more than 2 values. There's a good reason we call it the line of best fit and not the line of perfect fit. The equations we're finding are models for data that allow us to make approximations and predictions. They're not exact representations of data. Look back at the original table of fat calories near the beginning of this lesson. Use the calculator generated line of best fit to predict the number of calories in the Hardee's burger. So Hardee's. Okay, so this is the predicted. And we've got the actual. And we actually really want. And so our difference. So let's go to the Hardee's. The actual was 310. And the Hardee's grams was 12. So we want to go to the predicted. So if the actual was 310, and if we go to Desmos and go over to 12, it was 290. So they want us to find the difference between the actual and the predicted. So we're going to do actual minus predicted. And you can see that there's a formula. This is called residual down here in the purple. The residual is the difference between the actual value and the predicted. It's always the actual subtracting the predicted. Okay, so this is residual. And so the actual is 310 and the predicted is 290. And so there's a 20 difference. That's a pretty close, that's a pretty good fit. Now it says, when using a line of best fit to model the data, we use the term residual to refer to the difference. So now let's do this again. Find the residual for the White Castle burger. So the residual is the actual minus the predicted. So the White Castle was X equal to 7, and the actual was 140. And so if we go to our line at 7 grams, our line says 187 we'll go with. And so this time, the actual over predicted, I meant the line over predicted because we have a negative 47. So let's write that, our line over predicted. So it didn't predict the Hardee's or the White Castle very well. But it did predict the Hardee's pretty well up here. And that is the end of part 1 for 2.5. catch us back for the second part to learn a little bit more on some graphing and predicting and using our correlation coefficient.